AP Chemistry. Due to the fact that my website is on my computer that died this morning, we are going to be putting this podcast on YouTube, and so it is only going to cover electrochemical cells under non-standard conditions. We're looking at potentials in cells that are not standard, and we're also going to relate cell potential to the equilibrium constant for a reaction. On Friday, we're going to talk about electrolysis in class, and here at the end of the podcast, I'm going to give you guys some problems I would like you to do dealing with these concepts, in addition to the ones I assigned out of the book the other day. Do not worry, they're not very difficult and will not take you very long. So let's get to it, because we only have 10 minutes on YouTube. Okay, so we're going to look here at how to deal with galvanic cells in particular when they're under non-standard conditions. Okay, so in class what we talked about was the standard potentials of electrochemical cells, meaning that the concentrations are 1 molar, and also we're working under conditions 298 Kelvin. Well, that's really kind of rare to have 1 molar concentration. So in any other circumstance, if you want to find the potential of a real cell where the concentrations of the electrolytes are different than 1 molar, you use the Nernst equation. And the Nernst equation looks like this. What it says is that the potential for the cell, so symbolized with the letter E, but notice there's no degree symbol, the E for the cell is equal to the standard potential, which is E naught, minus 0.0257 volts over N, where here, this N, this is the moles of electrons that are transferred here during the reaction, times the natural log of Q. You may remember back to chapter 16, 17, 18, and 19, and 20 actually, that Q here, this would be the reaction quotient for the reaction, because just like we have learned in class, guys, every chemical reaction is in principle going to be reversible. So let's look at an example of how we would apply the Nernst equation. Here we go. We're going to determine the cell potential at 298 Kelvin for the reaction iron metal plus cadmium 2 plus ions yield iron 2 plus and solid cadmium, where under these two different sets of conditions right here. So let's go through and do that. So the first thing we need to do is we're going to use the Nernst equation, which, just to recap again right here, the potential for the cell is equal to the standard potential minus 0.0257 volts over N times the natural log of Q. So what we have to know for this cell is we have to know what, first of all, a good idea would be to calculate the standard potential for the cell. So to do that, we have to identify what is going to be the oxidation half reaction and what is going to be the reduction half reaction. I encourage you guys here to pause the podcast and to do that by yourself. But if you do not do that, you can just look at your table of standard reduction potentials and figure out which one of these two things, iron 2 plus or cadmium 2 plus, is higher on the list. Because iron 2 plus is higher up on the list, this is going to be the reduction half reaction because it is more spontaneous, okay? So, completely the opposite, actually. Iron is not going to be reduced. Iron is going to be oxidized. Cadmium here is going to be the reduced species. So if we calculate the standard potential right here, for the oxidation reaction, iron goes to iron 2 plus plus 2 electrons. The standard potential for that step is positive 0.44 volts. If you look at the reduction step, so cadmium 2 plus 2 electrons goes to cadmium metal, the standard potential for that step is going to be negative 0.40 volts. Okay, so if we add those two steps together here, we get that the overall potential for the cell is a mere positive 0.04 volts. It has a very small standard potential. Now let's look here at this first set of conditions. This would be the potential for the cell if the concentrations of these two electrolytes here were both 1 molar. But we can see that under both these situations we are considering here, the concentrations are not 1 molar. So let's go through and calculate the potential for the cell with these concentrations. Okay. Next slide. Alrighty. So I'm just going to write this down here again. Okay, our standard potential for the cell was, from the last slide, 0.04 volts. Okay, the other thing we need to know in order to calculate the potential under the conditions that we have, look, we're just going to look at part A here. Okay, we know here that in part A that the concentration of iron 2 plus ions from the problem is 0.010 molar, and we know that the concentration of cadmium 2 plus ions is 1 molar. Okay, now to calculate the potential, or not the standard potential, but just the potential here under these conditions, we have to know the value of Q. Q is the reaction quotient. And for this reaction, if we look here, the species, if we write the form of the reaction quotient, okay, for that reaction, it's going to be the concentration of iron 2 plus ions, okay, over the concentration of cadmium 2 plus ions. It's products over reactants. Again, the solid cadmium and solid iron do not appear here in this equation because those concentrations do not change. If we just plug that baby into the equation, it's 0.010 over 1, so we get a value of Q is equal to 0.010, and there we have it. So there's our Q value. Let's plug this all into the equation. So E is going to be the standard potential, which is 0.04 volts, minus 0.05, okay, 0.0257 volts over N. N in this case, because 2 moles of electrons are transferred for every mole of reaction, is going to be 2, okay, and then this whole thing times the natural log of Q, which is 0.010. If you guys plug this into your calculators and you calculate the value of E for the cell, you can see that the value of the potential is going to be 0.02 volts. So this, you can see, is even lower than the potential under standard conditions. The reason for that is because the potential for the cell does depend on the concentration. And you can see here it also depends here on the value of Q. If Q is 1, then what that means is that this term here, the natural log of 1, is 0, actually. And so this whole thing here would be the same as the standard potential. Whereas if Q is greater than 1, then this is going to be higher than the standard potential. And if it's lower than 1, then the potential under the conditions are going to be lower, is going to be lower than the standard potential. So there you go. That's how to calculate the cell potential under non-standard conditions. You could do the other half of the example, I am quite confident, by yourselves. Okay. One application of this idea, the fact that potentials are dependent on concentration, is you can make something called a concentrated cell. Okay, we're going to draw a diagram here on this next slide here. These are used for low voltage applications because they make a very low voltage. Okay, let's draw a picture. This is going to be a concentration cell. So I would have here in this compartment here, we have another compartment here. This compartment is going to contain silver ions. Okay, silver ions, and we're going to have in this compartment here a silver electrode. Okay, so imagine this is a silver electrode in there sitting in a solution of silver ions. Over here, okay, we're also going to have an aqueous solution containing silver ions. And we are likewise going to have an electrode in here which is made of silver metal. And of course, just like we've seen before in class, guys, both these electrodes here are going to be connected by a wire. They're connected together by a wire. And both these two compartments are going to be connected by a salt bridge. Okay, there's a whole lot of space to draw the salt bridge, but we'll imagine, okay, imagine guys, this is our salt bridge right here that connects these two cells. Now, what's going to happen in this cell right here, okay, or actually what's the difference between these two halves? Over here, our concentration of silver ions is going to be 1 molar. Over here, the concentration of silver ions is going to be 0.1 molar. Now you're saying, well, Mr. Harper, both these cells, or halves of the cell, contain the same thing. And I'll say, well, yes, you're exactly correct, except the thing that is different about these two cells is the concentration of the silver ions. Here on the left-hand side, it's higher, and here on the right-hand side, this is lower. And so actually, there's going to be a potential difference between these two halves of the cell, okay, and what the system is going to want to do, this is not at equilibrium. In order to achieve equilibrium, there's going to be a redox reaction. Okay, and I think